Okay, let's sum up what we get with thin film interference. Now again, ray 1 is going to travel a particular distance, ray 2 is going to travel a different distance. The difference in the distances is twice t. Now, twice t, we can relate it to the wavelength of the light in that film. So twice t is m lambda. Normally, when m times lambda, with m being an integer, whenever twice t is equal to m lambda with m being an integer, we get constructive interference. That's what we expect normally for interference. But because of the changes in phase in reflection, we are going to have different cases here. Now, what are the different cases? First, before getting into that, remember that lambda is actually lambda within the film, the wavelength of the light within the film. And remember, lambda within the film is going to be lambda in vacuum over n of the film. Now, let's take different cases. If we start at a medium with an index of refraction n sub 0, usually we are talking about air, but not always, and we move to a medium where we have a larger index of refraction, n0 smaller than n1, then the beam is going to slow down, so ray 1 upon reflection is going to be inverted. Now, if n2 is smaller than n1, meaning that the light is going to speed up when it gets to this medium, then beam 2 is not going to undergo a phase change upon reflection here. So we have only one phase change that happens here. Remember that there is no phase change upon transmission. The phase change happens only upon reflection. So it means that beam 1 had undergone a phase change and beam 2 didn't undergo a phase change. So this equation then, instead of giving us constructive interference, is going to give us destructive interference. Now, of course, the equation for constructive interference in that case would be twice t is equal to m plus 1 over 2 times lambda, with m taken 0 lambda film, of course. With m taken integer values of lambda. So twice t would give us, for m equals 0 lambda over 2, then 3 lambda over 2, and so on. When twice t is lambda over 2 or 3 lambda over 2 or whatever, then that would give us constructive interference. Okay, now, excuse me. What if we still have n0 is smaller than n1, but n2 is larger than n1, meaning that light is going to slow down even further when it gets to n2. What that means is we have a change in phase here and another change in phase here. So both of them are going to undergo a phase change, so that evens out. Then this equation is going to give me constructive interference. To get destructive interference, we are going to use this equation. Twice t is equal, let me try to write it in a cleaner version. Twice t is equal to m plus 1 over 2 times lambda film. Lambda in the film. Okay, so this would be my condition for constructive interference, and this would be my condition for destructive interference. Now, what if n0 is larger than n1? Then that's different. That means beam 1 is not going to undergo a phase change. Now, if N2 is also smaller than N1, N2 smaller than N1, it means ray 2 does not undergo a phase change either. So neither one of them undergoes a phase change. So this equation is going to give me constructive interference. Destructive interference, I can get it with this equation. Now, if N0 is again smaller than N1, ray 1 does not undergo a phase change. But if N2 is larger than N1, the beam slows down when it moves to N2, we have a phase change here. So one of them undergoes a phase change, that's ray 2. Ray 1 does not undergo a phase change. So this equation does not give me constructive interference anymore. It gives me destructive interference. To get constructive interference, I use this equation. Okay? Let's try to work some examples. Okay, what we have here, I'm not sure how blue is this 500 nanometers. That's not very blue, but let's just take the values that I have in this slide here. What we have, it is incident on a glass cover slip. The index of refraction of glass is 1.5. Of thickness 167 nanometers. That is floating on top of water that has an index of refraction of 1.3. Is the interference constructive or destructive or neither for this particular thickness? Okay. So what we do is we calculate twice times the thickness. Twice times the thickness, that's 2 times 167, so that's 300, and let's see, 67, so 320, 334. Nanometers. Now the medium here is glass. That's where the path difference is occurring. So this 334 nanometers, we should relate it to lambda inside the glass. What's lambda inside the glass? Lambda inside the glass is going to be 500 nanometers divided by 1.5. Okay. 500 divided by 1.5. I'm calculating it separately here. That's 300. 333 nanometers. Okay, so here we have m times 333 nanometers. So m is approximately equal to 1. Okay. Now the path difference is equal to a wavelength of the light inside that medium. Now, if there is no change in phase, we should have constructive interference, since both rays are going to be in phase. But now what do we have? We are going from air to glass. So the wave is going to slow down here. So in this case, I have a phase change. So let's make a check for a phase change. Here, when I move from here to here, I move from glass to a lower index of refraction, meaning that the light is going to speed up. If it's going to speed up, I don't have a phase change, which means I have a phase change for ray 1, no phase change for wave 2, for ray 2, which means this condition, twice t is equal to lambda glass, is not a condition for constructive interference anymore. It is destructive interference. So in this case, we have destructive interference, meaning we will not see that light. Let's take another example. In this case, we are using the same thickness of glass, but we have here plastic instead. Start an air, glass, plastic. So we go from a low N to a higher N here, which means we have a change in phase here, and we have another change in phase here. So it evens out. The change in phase evens out. So twice T is equal to M lambda glass is going to give us the condition for constructive interference. And we have it here with M equal 1. So that means we have constructive interference. Now let's take this other case. What we have here, we have some water of index of refraction 1.3, and we have a layer of gas here of index of refraction 1.2, and a layer of oil of index of refraction 1.45. Okay. Now the question is, when the thickness of the film, this film or this film, is exactly one wavelength, the gas would look bright or dark? And then the same question for oil. Okay, now in this case, for the gas, we are going from air to gas to a higher index of refraction. So we have a phase change, and then here from gas to water, a higher index of refraction, so we also have another phase change. So the phase changes even out, and twice T is just equal to twice lambda, since T is equal to one wavelength, and I'm assuming here the wavelength inside that film. Now, if twice T is equal to twice the wavelength, the two rays are going to be in phase. We don't have the phase changes even out, so I should get constructive interference, so it's going to be bright. Now, in this case here, in the case of the oil, we have a phase change here, but we go from a high to a lower index of refraction when we move from oil to water, so no phase change here. So twice T is equal to 2 lambda, but in this case, we have a phase change for one of them, but not for the other. So this condition is the condition for destructive interference. So my oil patch is going to look like dark. Now, some pictures here. How does this look like in nature? This is a very clever, actually, device from the same website. These here are calculations as the thickness of the film is going to increase. Think of this as like a soap bubble. As the thickness increases, when there is no thickness at all, one of them is going to flip, the other one is not, so we are going to have destructive interference. And then constructive or destructive depending on the wavelength of the light. And actually, how do you accomplish that in real life? What he did is he set up like a soap bubble on a frame, on this rectangular frame, and held it vertically. So when he held it vertically, because of gravity, then the film is going to be thicker at the bottom than the top. The thinner one, you see it here dark, and then here we have constructive interference for red, here for blue, and so on. White, that's when all light beams are going to add up. That's when it is constructive for all. Now in nature, like this is a thin film, what we have is air. Actually, let me go back to the soap film. So in the soap film, what do we have? Air, film, air. So my third medium is the air, which is very much like when we go from something like this to like this. So we go air, low, high, then low. So that's what we have. Low the air, film high, and then we go back to low. Same thing here with a spider web, and that's why we see these different colors that you see there. And that's so that depends on the thickness of the film and the angle we look at it, because with the angle, the thickness that it's going to travel through, that the light rays are going to travel through, is going to be different. If I'm looking at it like this, the beam is going to move like this. If I'm looking at it straight on, it's going to move like this. Now a peacock, now the different colors in the feathers are also due to moving from air to the feather and then back to the air. And actually it's a little bit trickier than just that for the feathers. There is a structure involved. Same case with the duck here. In mosquitoes, the same kind of ideas. And actually, when you look at a beetle like this at a different angle, you see different colors because of the same reasoning that we discussed here.